Hi, this is Terrence, and today we are going to talk about lasers. So let's get started. So this here is the laser that we currently have on loan in the space. I've been fixing it and fixing it and fixing it again for quite a while now. And well, I've gotten really good at fixing it. When we built our new lasers, we're going to do a few things differently. So let's talk about how this laser works and how we're going to do things a little differently. So in this particular laser, we have a laser tube here. This essentially, when the laser fires, the high voltage power supply sends about 25,000-ish volts through it. It's called striking the tube. That ionizes the nitrogen and CO2 gas inside the glass tube that you see here. And then the laser beam fires out, hits the first mirror, comes up, hits the second mirror, bounces down into the third mirror, and then down into the object that we are cutting. Now, there's a couple of things that aren't great with this particular setup. So for one, these mirrors are exposed. And so the way laser optics fail is when dust gets onto them and then the laser beam hits it and it causes a reaction between the dust particles and the laser mirror substrate, and that's how the fouling occurs. And in fact, if we were to zoom in, you may not be able to see it, but there's a little bit of debris or haze on the mirror. And that's basically indicating that the lens has already been fouled a little bit. It doesn't help that this is right by the exhaust gas port, right? So all the air that's coming in is being pulled up with all the dust and debris, and it's being pulled past the exhaust, past the first mirror here, into the exhaust port. Oops, excuse me. So yeah, as I was mentioning, one of the problems of this setup is this is where the exhaust gas port is, and so all the air that's being pulled in is being pulled past this primary first mirror, and then past the exhaust gas port. Well, this air is laden full of dust and debris, and so you can imagine how easy it is for the first mirror to be fouled. The second problem is we really want to be running these lasers under negative air pressure, which means that the amount of air that you pull out through this port has to be bigger than the amount of air that you're pulling in into the box. Now this is inherently problematic because, as you can see, this is the radiator assembly that is attached to the coolant pump. And you really want to be flowing a lot of air over this radiator assembly in order to pull the heat out of the laser tube. But you are limited by the amount of air that can be pulled through this tube. Remember, the amount of air that you're pulling in past the radiator has to be less than the amount of air that you're pulling out through the exhaust vent, or you're going to go into positive case pressure, and then all the dust and debris and laser-generated airborne contaminants get pushed out of the case. So, so inherently, our lasers are underpowered. Probably for that reason, right? When we were working on the 65-watt laser, I did some optical measurements, and I found out that the 65-watt laser at full power only was outputting about 17-ish watts or so. A laser tube is approximately 10% efficient, which means for every watt of power that is coming out through the optical end here, making the cut, about 9 watts of power is being lost. And really it's not lost, it's just being dissipated as heat, right? So this water jacket that is circling the water through and coming out has to remove, for a 40-watt laser, about 36 watts of heat. If you look at the spec sheet, numbers get even worse from there. The spec sheet calls for about 20 to 25 degrees to 25 degrees centigrade water temperature. But on a hot day here in Everett, we can be walking in and that tube is already at 27 degrees. So there's really zero headroom. So what are we doing different? Well, for once, we are going to be water cooling our lasers with an industrial water chiller. So thanks to Kenneth for donating this. This is an industrial water chiller, and its only job is to basically take a big body of water and cool it as much as possible using a refrigeration cycle. So mechanically, this is actually a fridge combined with a heat exchanger, and it pumps water, cold water, through the laser tube. So we're going to plumb this directly into our laser in order to remove the heat from the tube. The other thing we're going to do is we're going to encase the laser beam. So instead of mounting the laser tube all the way in the back, we are going to mount the laser tube on our gantry, and the laser tube is going to fire into a mirror box. So like this. And then into our cutting head, where it goes, the laser beam then goes into the plane of the display. There's a few advantages of doing it this way. So because the box here can be enclosed, we can actually make a gas-tight coupling between the laser tube and the box. And this way dust will never get in to foul these two mirrors. Now what we will do is we'll put a optical window here and here on the head, because this can move, and so this head can sit at various different distances away from the mirror box. So we'll put a window in front of the exit end of the optical box and the entry end of the cutting head. Zinc selenide is a good material for this because it is transmissive in both the 10.6 micrometer wavelength that the CO2 laser is firing at and the 650-ish nanometer wavelength that the red diode is firing at. Now, to make this work, we will have to kinematically mount this laser tube so that we can adjust for tip tilt. So the lenses will be rigidly coupled in place at 45 degrees, but because the laser tube is hand-blown glass, we can't be assured that the beam coming out of it is going to be concentric to the output to the housing of the laser tube. In fact, I guarantee you it's not going to be. But what we can do is we could put the whole laser tube on a kinematic mount that allows us to move this laser tube and also to tilt it relative to this glass mirror. So as long as we can get this beam dialed in, we can then get it to fire properly into the mirror head without alignment issues. Now, obviously, I'm not the first one to come up with this layout. There's been builds on CNC laser forums and such with putting the laser tube on the gantry. A company called Glowforge that I used to work for popularized this with their Glowforge and Glowforge Pro laser cutters. So it's definitely a tried and true design. We're just scaling it up a little bit to use a bigger tube in our particular laser build to do this. So the advantage of doing this way is you're not going to have any sort of mirror fouling issue. So this is an example of the fouled first mirror that you see on our laser. Because the optical path is sealed, dust won't be able to get in, so this wouldn't be a problem. The other advantage is that if you do need to replace parts, these two optical windows don't carry any sort of special alignment requirements. So we should be able to just unscrew the optical window. If these do get fouled, we can unscrew it and screw a new part in without having to go through the recalibration process. The disadvantage is that by putting this laser tube on a moving gantry, we complicate the wiring a little bit. So both the water coolant in and outlet tubes, as well as the high voltage cables, need to now go through a cable chain. For the water cooling tube, that's probably not too much of a concern. For the high voltage wires, you have to find a high strand count and a high voltage dielectric wire. Fortunately, I found one. This is what I found on McMaster car. 18 gauge, high strain count, so it's a continuous flex wire. 168 strands of 40 gauge wires woven in an 18 gauge wire. That's rated to a dielectric strength of 42,000 volts. So let me show you how this looks in CAD. My CAD is still very much a work in progress, but let me show you the kinematic mount. So this is going to be a 3D printed part. It's going to have 4 of these basically pushers on it, and there's going to be 2 of these mounting the tube. They're going to sit roughly at the 1/3 and 2/3 mark on the laser tube, and the way this works is 2 of these are going to be spring loaded, so there's going to be a spring behind it pushing on this. This is a rubber ball, so we have a ball on spherical surface contact for single point contact. And then on the other side, there's going to be a set screw of some sort pushing against the ball. So normally the springs will spring this tube all the way out this way and all the way up this way. But then we can adjust the adjustment screws to dial the X and Y position in on both of the mounts, on both of the mounts independently, and by that we can both move and rotate the laser beam coming out relative to the mounts. Our goal is to basically have the laser hit the same spot on the cutting head, regardless of where the cutting head is on the x-axis. And that's going to tell us whether we have the laser beam parallel to the x-axis travel or not. In fact, we're going to do 2 adjustments. We're going to first move this carriage all the way up close and then adjust this set of screws here to center the beam on the entry aperture of the cutting head. And then we're going to move this cutting head further down here and adjust this set of adjustment screws so that the dot still remains centered on the cutting head. And then by moving it back and forth, we could test it and test it for alignment. One other thing that I want to point out, again, thanks to a generous donation from Kenneth, we have 2 of these SPT red dot laser tubes. So these tubes are really cool. SPT managed to figure out how to put a red dot sighting laser collinear to the path of the CO2 beam. And so we actually don't need to test fire the CO2 laser at all to do our alignment. We have a red dot that we can use for optical verification of the alignment of the laser. So that is very, very cool. And we also will be able to have the red dot in the cutting head for tracing or framing operations when we are setting up a job on the laser. So that's it for this video. Next video, I hope to share a little bit more with you the CAD and talk a little bit more about the motion control system that we're putting into the CO2 laser, as well as some of the interlocks and safety features that we're going to roll into them. So thank you for watching. If you like what you're seeing, please like and subscribe and help me get the word out. Thanks. Bye.
Beep boop, beep boop.